In addition to storing single numbers, R can store several numbers in the same object we call a vector, or more properly, an atomic vector. To tie these numbers together, we wrap them in a C, like this, C246, and we can evaluate it, and that's what it prints out like. We can also store them to variables, like this, x is C246, and then when we refer to x, it pulls up the same vector that we stored. We can check the length of the vector with the length function, length x. The entries of x are called its elements. So 2 is its first element, 4 is its second, and 6 is its third. We'll come back to that in a little bit. It's helpful at the outset to differentiate atomic vectors from lists, which are different kinds of vectors. Lists are made with the list function, like list 2, 4, 6. Notice that lists are very different. They're made differently, and they print differently, even though they too are technically vectors in the R language. Usually when people refer to vectors, they mean atomic vectors in the C sense. But just know that lists are formally vectors also, but almost nothing we do in this video will work with lists. To start, we can do arithmetic with vectors, just like ordinary numbers. So x plus 2, x times 2, x squared, and so on all work with atomic vectors. Comparison operators also work to create vectors of logicals, also called booleans. More on this in a moment. But as an illustration, I could do something like x is greater than 3, and I get a vector of trues and falses back. Or x is not equal to 4, and I get a vector of trues and falses back again. Many math functions also apply element-wise, so if I take x times pi over 8, there's nothing special there because pi over 8 is simply a number, and we already know that vector number arithmetic is already defined. But if I put this in the sign function, x times pi over 8, we see that I get 2 pi over 8, i.e. pi over 4, 4 pi over 8, that's pi over 2, and 6 pi over 8, that's 3 pi over 4. The exponential function works, as does the log, and so on. We call functions that operate element-wise vectorized, and most of the basic arithmetic functions in R are vectorized. Now, the arithmetic and comparison functions are also defined between vectors, so if I create a new vector, y is C751, I can add the two vectors, or I can subtract them. I can even use the modulo operator between them. All of these functions will work. I can also use the comparison operators, so I can check x is greater than y, and I get a vector of logicals back. In fact, there's a special way to do max and min over two vectors. Pmax takes two vectors and will give the pairwise maximum through each of the elements. So if I look at x and y, the maximum of 7 and 2 is 7, the maximum of 4 and 5 is 5, and the maximum of 6 and 1 is 6. There's similarly a pmin function xy, which picks out the parallel-wise minimum. Since vectors usually contain measurements on different objects, for example, the different heights of different people, many statistical functions are defined over vectors. So if I make a new vector C34152, there are lots of statistical functions that operate on t. For example, I can take the sum of t with the sum function, or I can multiply all of the elements of t together with the prod function. I can compute the cumulative sum with cumsum t, that's 3, 3 plus 4, 3 plus 4 plus 1, 3 plus 4 plus 1 plus 5, and 3 plus 4 plus 1 plus 5 plus 2. I can also take the cumulative product of t. I can take the cum max of t and the cum min of t. I can even difference the elements of t. What this is the pairwise difference between neighboring elements of t. So the first element 1 is the difference of 4 minus 3. The element 2 is 1 minus 4, and so on. So when you difference, you always lose one element. The difference of the length 5 vector t is a length 4 vector. If I want to summarize the entire vector, I can use max of t, that picks out the largest element, min of t picks out the smallest. I can sort t with sort t, and it sorts it from smallest to largest in so-called ascending order. If I want to sort it from biggest to smallest, I say sort t, decreasing is true. Lastly, if I want to find the ranks of the elements of t, I can use the rank function. As you might expect, there are many statistical functions in R. In terms of the descriptive measures of center, we have the mean of t, the median of t, and the mode of t. That didn't seem right. What's actually happening there is that we're seeing a conflict between R as a programming language, where t is a vector of type numeric, and R as a statistical programming language, where you may think that mode is the most frequently observed value of the vector. To get something like that, we would use the table function. The table function will tally the number of times that each of the observations in the vector is observed. In this case, every number is simply observed once. For measures of dispersion, we have the standard deviation of t and the variance of t. The range of t, which here is actually two numbers, the smallest and the largest number in the data set. In statistics, usually the range refers to the difference of these, so we would use the diff function on this to get 4. There are also other measures of dispersion, such as the IQR and the MAD of t, but we won't go into these anymore. In addition to measures of center and dispersion, we also have measures that I like to call measures of accumulation, by which I mean percentiles. So if t looks like this, percentiles are computed with the quantile function. Quantile t, let's say that I want the 50th percentile, or the median. I can also compute other quantiles, for example, the 25th percentile, the number such that 25% of the data is less than it. I can even put a vector of quantiles in here and compute many percentiles at once. They're returned to me as a vector. Another thing that we can do with vectors is plot them. When we plot them, we get a scatter plot, that's a plot of points, where on the y-axis we have the value of the vector, and on the x-axis we have the index. So the first element is 3, the second element is 4, the third element is 1, and so on for all of the elements. Now, vectors aren't just a collection of numbers, they're an ordered collection of numbers. We can extract the individual elements by using the hard brace operator, along with their indices. This is often called subsetting or slicing. So if this is t, t1 is the first element of t, t2 is the second element of t, t3 is the third element of t, and so on. I can subset with negative indices to throw away that entry. For example, t hard brace -2 discards the second element and returns the result as a vector. Working with indices in R is a really common thing to do. So there's a function called which.max of t, which tells us the index of the largest element of t, and which.min of t, which gives us the index of the smallest element of t. In addition to subsetting or slicing by one number, I can actually subset or slice by a whole vector. So t, c, 2, 3 gives me the second and third elements of the vector t. The function order t gives us the vector that, when I subset t by it, sorts the vector. For example, t order t sorts the vector in ascending order. Now, apart from C, there are actually many other common ways to make vectors in the R language. Maybe the most common is the colon operator, which makes a range of numbers. So 0 colon 10 gives 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I type in SEQ for sequence, I can do the same thing, but in a more extensible way, or in a way that gives me more flexibility. For example, instead of going by ones, I could go by 0.5. Now I have 0, 0.5, 1, 1.5, and so on. Alternatively, I can specify the length of the ultimate vector that I want by specifying length.out is, and I'll say 31, which is maybe not so pretty, so I'll say 101. Another way to make a vector is with the sample function. Sample 1, 0 to 10, 5. This will take a simple random sample without replacement from the sequence of numbers of 0 through 10. Here, every number is equally likely. If I want to take a simple random sample with replacement, I need to say replace is true. Now, as you can see in this example, I drew the number 3 2 times. If I had replace equals false, I couldn't do that. When we deal with random numbers, one of the things that we want to do very commonly is to set the seed. Set seed to 1. An advantage of this is that it will allow us to synchronize our random number generators across the computers. So for example, if I run this chunk of code as many times as I want, I always get the same result, even though I'm using a random number generator every time. On the topic of random number generation, R has a number of random number generator functions for probability distributions. While these are generally outside the scope of this particular video, they all follow a consistent naming pattern, which is R followed by the name of the distribution and then open and close parentheses. For example, if I want to sample from the uniform distribution, it's R, U, and IF, 10. This will give me 10 numbers between 0 and 1, with each number being in some sense equally likely. If I wanted them from a normal distribution, or the bell-shaped distribution, it's R norm, 10. Now it's worth talking for a minute about vectors that aren't numbers. As we've seen, R can also have vectors that aren't numbers. We've actually seen this before with trues and falses. For example, I can make a logical vector explicitly with true, false, true, or I can even make it like this, TFT, but this is discouraged in the R language because you can assign T a different value. And that's a really bad idea. So we won't use the shorthands T, F, and T. Actually, logical vectors are rarely made explicitly. They're usually made implicitly through comparison operators. For example, here's the vector 1 through 4, and I can compare A to 2.5. Obviously, 3 and 4 are bigger than 2.5, and 1 and 2 are less than 2.5. So I get a logical vector of false, false, true, true back. I can also subset by that expression. For example, I can say A where A is greater than 2.5. Subsetting by a logical vector returns the elements of the subsetted vector where the elements are true. In this case, that's 3 and 4. It's a really useful way of extracting data from a vector that satisfies a particular condition. Now, there are also some functions that are only really useful in logical vectors, like the function any, a is greater than or equal to 2.5. That will ask, are any of the values of a bigger than 2.5? Obviously, the answer is true. There's also a function called all. Are all of the values bigger than 2.5? And the answer, of course, is false. When we try to do arithmetic with logicals, trues become 1 and falses become 0. Again, the use case is in terms of logical vectors that are typically determined implicitly. So for example, I could say how many elements of A are bigger than 2.5? A is greater than or equal to 2.5, and then I can sum them. When I do that, the last two elements that are true both become 1s, the falses become 0s, and the sum is 0 plus 0 plus 1 plus 1, which is 2. A very, very common use case of this is actually with the mean function. When I average a whole bunch of numbers that are either 0 or 1, what I get back is the proportion of numbers that are 1. So in this case, 2 out of 4 of the numbers in A are bigger than 2.5, and the mean is 0.5, or 50%. So now we've seen vectors of numbers and vectors of logicals. We can also have vectors of characters, but we need to take a step back a moment to see what characters are. Characters are often called strings, and are input with 2 quotes. So if I type in hello, this is a string in the R language. It can also be input with single quotes or apostrophes, and those are exactly the same thing. Note that that's different than the backticks, that's the button above your tab on your keyboard. That's going to refer to a variable named hello, and we haven't defined one. So it looks for it and says it can't find it. I can create vectors of characters using the exact same syntax. So hello world. That's a character vector of length 2. We'll see character vectors a little bit later on, but usually in data analysis they're useful for things like storing addresses or names. As you might suspect, arithmetic operations aren't defined between characters, so I can't say hello world and get anything useful back. Similarly, I can't take the average of a character vector like this because averages with characters are not meaningful.